Namaskar and good day to all. Day 2 with a topic of electric field and if possible electric potential also. This is what is electric field, which you know very well. The space around any charge or distribution of charge or any system of charge. Now electric field intensity is always defined at a point. And this is E bar, intensity vector, as F bar by Q naught. F bar is the Coulombic force and Q naught is the test charge. It's a vector quantity, do remember. So in all intensity examples, it is most essential to use electric intensity as a vector quantity. And the direction of intensity we will provide in all the individual cases in the tube course. Now here the SI unit is Newton per Coulomb. Otherwise we also take it as volt per meter. This is volt per meter. And the electric field is always represented by field lines. About the properties of field lines, you can go through our class notebook. Now, this electric field, it can be either uniform electric field or non-uniform electric field. In all our cases for CT and NEET, we always come across uniform electric field. Now here I have given a representation of that uniform electric field as straight, parallel, equidistant. Only this representation will tell you that the field is uniform. Any other form, supposing if I show a field like this, or in any other manner, it becomes a non-uniform electric field. Therefore, this one is the uniform electric field. Intensity is same at each and every point, both in magnitude and direction. Now here, let us come to examples that are possible with the electric field. Now here is a very famous title. It is charged particle in an electric field, and as I have told you, it is a uniform electric field and charge is initially placed in the electric field that without any initial velocity. Hope all of you can see the board. Now here, whenever a charged particle is placed in an electric field, the first point is it experiences force. And by the definition of electric field, now you can write the force as F is equal to EQ. In fact, this is F bar is equal to E bar. And this force giving rise to acceleration, F equal to ma, A is equal to F by M. So one more time, this is also A bar is equal to E bar Q bar M. Now, the most important point is, what will be the direction of this force and acceleration? Now for that, I just show you. Now you can please do this. Supposing if I have placed a charge Q here, it's a particle with mass M and charge Q. I am using these symbols with their regular meaning. Q is the charge of the particle and M is the mass of the particle, right? So now supposing a charged particle is placed over here in this uniform electric field, you can see the field is towards your right hand side. Then if this is a positive charge, it will experience force along the field that is towards your right hand side. And if it is a negative charge, it will move opposite to the field. Do remember, positive charge, force is along the field, and for the negative charge, the force is opposite, anti-parallel to the field. Right? Now, with this acceleration term, now let us come to some kinematic points like velocity the particle has acquired. Same kinematic equation, you will use V is equal to U plus AT, where you are taking the U term to be 0, or V square minus U square equal to 2AS. Now, use this A in those equations, like V is equal to AT and V is equal to root of 2AS. This is velocity time relation and this one is velocity velocity displacement relation. Now, since velocity is known, we can now write it for the energy acquired by the particle. That energy is the kinetic energy acquired. So kinetic energy half mv square. Now you have this v here, we can substitute here. Do remember, these are not the formula to be by hearted. Only thing is that the force and acceleration afterwards this velocity v is equal to at and the velocity v is equal to 2as as for displacement. Now those expressions that we have given for charged particle placed in an electric field. See here, I show one simple example, very popular. Now we know that force F is equal to EQ. Supposing 2 or 3 different particles are released or placed in same electric field like electron, proton, alpha particle like that. Then which will acquire more force, which will acquire same force or which will acquire least force. All such cases you can find here the simple ratios I have taken, right? F is equal to EQ, so F1 by F2 equal to Q1 by Q2 independent of mass. And therefore here A proportional to Q by M. Because all the particles are considered in the same field, therefore now here A1 by A2 is Q1 by Q2, but it is M2 by M1. And similarly for the velocity expression also. Velocity time relation is EQ by M into T. Remember, and velocity displacement relation we have told that is root of 2a s, a term is eq by m. And similarly, when it comes to energy also, suppose if it is energy time relation, then what here you find is k proportional to q squared by m for a given data of time, whereas same kinetic energy for a data of displacement if it is given, what you find is k proportional to only q here, independent of mass. So in all the expressions, this is the case for different particles placed in same electric field. Comparison of forces, comparison of accelerations or velocities or energies. Now you see, I am giving you some simple examples how we are making use of this force on a charged particle in an electric field. We have seen this expression F is equal to EQ. Now, one simple example, electric force versus gravitational force I am discussing with you. For that, I have considered this is suppose a very tiny particle or an oil drop or a tiny sphere. I have considered it as a spherical body. It's a very, very tiny particle. And of course, I am using the regular terms. L is its mass, R is the radius of the drop, Q is the charge. On the drop, it can be either positive charge or negative charge. Right? Now, this oil drop or the tiny particle is balanced in A. The data says the oil drop is balanced in A by an electric field. So here I have shown this is the oil drop, charge level, balanced by an electric field. Remember, whenever I am using electric field, it's always uniform electric field. Now here, the balancing condition I am writing, mg is the downward pull. So any particle balanced in A, always mg should be balanced by an upward force. Remember, mg always balanced by upward force. Therefore here this F is equal to EQ is an upward force. So I am writing EQ is equal to mg. Now supposing if the drop has the charge due to loss of electrons or gain of electrons, I will write this Q as N is the number of electrons gained or lost. So this is how we get an expression for this N, number of electrons lost or gained. Now here, how to know whether it is loss of electrons or gain of electrons? It will be understood by the given electric field. Supposing if it is positively charged one, that is loss of electrons, is always balanced by upward electric field. And negatively charged one, that is loss of electrons, is always balanced by downward electric field. I repeat it. It should be upward electric field means loss of electrons, and downward electric field means gain of electrons. Suppose in the same example, asked in a different way. How? Instead of asking for the charge of this thing, now here you can see, zoom it please, saying EQ is equal to mg, where this m mass I have taken volume times density r for radius, 4/3 pi r cube is the volume, density times g. Now here I am writing an expression for the radius of the drop. You can see here I am writing an expression for r here. So it is cross multiply, you will get this 3 EQ by 4 pi rho z, and this is everything cubed root. So here as well, 2 or 3 different examples like this, like radius depending upon the field and also depending upon the charge. So this is the balancing electric field, the charge on the particle or the drop, or is the radius of the drop. Now you can find here, this is very popular thing that we have told. In any example, all RHS terms, what are the variables, what are the constants, and that simple lead will always give you a better idea of solving the question. One more example. Here you can see a simple pendulum, and this is the load. And in this case, the only force that it is experiencing is gravitational force, and therefore the only acceleration is g. And hence we write the time period, very popular expression, t is equal to 2 pi root L by z. Or if you take the reciprocal of that, you will get an expression for frequency. Now supposing, in this case, it is given that this is a pendulum whose load is a charged one. Again, it is either positive charge or negative charge. This is charged load and it is suspended in a region containing an electric field. You can look at this picture carefully. Load is charged. I have shown it as positive, but it can be either positive or negative, and this is suspended in a region containing electric field. Again, I have shown this field as upward. It can be either upward field or downward field. Now, how to calculate the time period of oscillation or frequency in this case, or how to compare these two things, supposing whether the time period increases or decreases. So, questions simple like that. Now, here you will find that in this case, G is downwards, it's a downward vector, and earlier I have told you this F is equal to EQ. Positive charge is always along the field. Negative charge, it is opposite to the field. Now, you only can write that direction. It's a positive charge and field is upwards. Therefore, G is downwards, and this acceleration A is equal to EQ by M is acting vertically upwards. Two vectors anti-parallel. So, what will be the net acceleration here? So the net acceleration is G minus EQ by M I am writing. Why this negative sign? It is because of the vector sum you can see here, right? G and A anti-parallel, therefore I am taking it as G minus EQ by M. Now therefore the new time period I am writing it as P prime as, yes, you only write it. This is 2 pi under root L by G minus EQ by M, right? G minus A term. So certainly you will find that this denominator term is decreasing. Denominator term is decreasing, therefore this time period will increase. Now I will say T dash greater than T. That is to say that the new frequency or the frequency in the second case is less than that of the case 1. Likewise, I have shown electric force versus gravitational force. So in the next example, let us see one more case where electric force is balancing, or electric force versus frictional force will be my next simple example. One more example of this electric force and charge. This time I have taken electric force versus frictional force. Now here is a rough horizontal surface. This is the rough horizontal surface whose coefficient of friction is mu static friction. This is placed on this horizontal rough surface. This is block of mass m and it is a charged block, supposing. And this is electric field applied. This is a uniform electric field. The space containing uniform electric field. Now here a condition is given. Now what is that condition? The condition can be asked either for charge, or the condition can be asked for either coefficient of friction. How? So what will be the maximum intensity, or what will be the minimum intensity required for this block to slide? So for the block to slide, what is the minimum electric field, or what should be the maximum or minimum condition for this coefficient of friction? Or even it can be a condition for either minimum or maximum. Let us see that. So this is the conditions for electric field, or the conditions for mu, or the conditions for q. Now here, what will be the condition for the block to slide? Again, please remember whether the condition for block to slide or not to slide is an important thing that you have to identify. I am writing it for block to slide. Then for such case, what will be the condition? Friction says don't slide, and F is equal to EQ says slide. Right? Therefore now what will be the condition for the block to slide? Then EQ should be greater than or equal to F. I am writing the condition for block to slide. Then the sliding force is EQ should be greater than or equal to the opposing force, friction. Look at this condition carefully. And the same as we continue. So this is EQ greater than or equal to, and we always know that frictional force, horizontal surface, then we write it as F is equal to mu times the normal reaction, which is mg here, right? So EQ greater than or equal to mu mg. Now here you always do remember, whenever you are writing a condition like greater than or equal to, convert it into equal to. Remember, greater than or equal to, convert it into equality, then you will always get the condition for minimum. Condition for minimum. Whereas less than or equal to condition when written as equality, we will get the condition for maximum. So this is a very, very important point to be remembered. We come across in every topic. Greater than or equal to when written as equality, then we get the condition for minimum. Less than or equal to, converted into equality, we will get the condition for minimum, right? Therefore now here, the condition for E will be minimum, right? So now we write a condition, what is that? E minimum. E minimum is equal to, this is mu mg by q. Again, the condition for Q will also be minimum. If I am writing conditions for charge Q, this is Q minimum is equal to, I will write it as mu m g by E. Right? Observe carefully, I am writing condition for different parameters here. Similarly, if I write a condition for mu, and do remember, this is greater than or equal to relation. If I am writing it for mu, it becomes less than or equal to condition, right? Because LHS and RHS interchange, then you will get greater than or equal to becomes less than or equal. Therefore, now here I can write the condition. Now you will be tell me, it will be the condition for mu maximum. So mu maximum. we have given conditions for E minimum, Q minimum, but in the case of mu, it will be the minimum. So mu minimum is EQ by mg. Got it? I am writing the condition for block to slide. If it is the other case, then you will have greater than or equal to becomes less than or equal to, then it will be a condition for not to slide. Got it? One more simple model, very popular model. Here again I have taken a simple pendulum. A simple pendulum whose load is, supposing it's a charged one, and I am writing it as positive charge, and you should not always think that it is always positive charge, can be negative also. Do remember, positive charge in the direction of field will be the force, and for negative charge it will be opposite to the field, right? Now here in this case, it is suspended in a region containing a horizontal uniform electric field, right? You can see here. As a result, what happens is this load, the bob of the pendulum, will displace from its mean position and attains equilibrium. He will ask you questions regarding the equilibrium condition, which now I am writing. Now here, in this case, this is what is equilibrium position. What is meant by equilibrium position? Net force should be 0. Now what are the different forces that are now acting over here? Now let us see. Now this is electric field and this is a charge, and therefore electric force F is equal to EQ. F is equal to EQ. Now here I am sure all of them in the vector form also. And then gravitational force is, this is electric force, and gravitational force is mg vertically down, and this one is a horizontal force. These two forces are not collinear, therefore no condition for equilibrium. There should be a third force as well, right? Now look at this. What will be the third force? The third force is nothing but the tension that is developed in the suspension, which I am writing as T. Now, another force is tension, which is acting towards point of suspension. Towards point of suspension is the third force I am writing. Now, always remember, now I have a vector diagram. I will show you this in the vector diagram, and we make use of a very popular law which we have learned in our first video, right? Now this is what is the case. This is the horizontal force, sorry, vertical down, mg. This is horizontal force, F equal to EQ. And the third one is, of course, the force of tension in the suspension. And these are right angles, right? Of course, do remember, we cannot get into the details, I hope you all remember. Leibniz theorem. What is the Leibniz theorem? F is equal to mg tan theta. Here is the vertical angle, theta, right? F is equal to mg tan theta, one condition. The other condition is P is equal to mg secant theta. Therefore, both, if you divide, you will get an answer as F is equal to T sin theta. So, this is the relation between the pain of the forces. Remember, F, horizontal force. In this case, the F is nothing but EQ. Therefore, our condition is EQ is equal to mg tan theta. The question can be given for any of the data. It can be asked for either E, you will write it, right? Or it can be asked for theta like that. Now I am writing it as tan theta is equal to EQ by mg. More examples regarding electric field. You will get it as an assignment. Please go through all your assignment very, very sincerely. And maybe yesterday, I don't know whether you got contact numbers. Today, at the end of the session, I will definitely share the contact number. Any of your doubts, do feel your free time to contact your teachers, right? Now, another topic regarding electric field would be the electric field produced by different system of charges. I am taking discrete charges initially, afterwards I will write it for continuous charge distribution. Now to begin with, here we will find the point charge. In field due to the point charge. Field due to the point charge. It can be either positive charge or negative charge. Please remember. Now here, what you find is intensity at a given point, which is at a distance r from the point charge. This is the expression you can find. 1 by 4 pi epsilon naught. A term that we've been using since Coulomb's law, the magnitude being 9 into 10 by 9. Q the charge and r square. You will find this relation E proportional to 1 by r square, right? Now here, this is not a simple scalar, therefore we should be very observant. It is a vector quantity, direction is very important. Here you will find positive charge, point P, the field you will find away from the charge. On the line joining, away from the charge. And for the negative charge, hope you all are keenly observing this. This is a point P at distance r from a negative charge, suppose, then the field intensity, the vector is towards the charge. Got the point? For a positive charge, it is always away from the charge, and in the case of a negative charge, it is always towards the charge. Right? This is essential because when we are given more than one charge, and in finding net electric field, we should always make use of vector addition, not scalar addition. We will come to those examples as well. Now in the case of dipole, again another discrete charge system, you always know about dipole. Please go through all our class notebook. You will find complete details regarding dipole. Now here it is the dipole, a system with equal and opposite charges with a finite separation. That finite separation I have taken it as suppose 2A I have taken as 2A, and this line joining the two charges in the center we call it as axial line. You remember this? This one is axial line and this one is another line passing through the center of the line and perpendicular to the axial line, which we call equatorial line. It is not equi, remember it is equatorial line. Now I am writing expression for intensity at axial point and equatorial point. Same term, 1 by 4 pi epsilon naught, and it is 2p by r. And in the case of equatorial point is 1 by 4 pi epsilon naught, P by R cube. And I have told you, please go through your class notebook, you will find, of course, what is that? Small p stands for? Small p stands for the length of the dipole times charge, and this is called dipole moment. We have no time for going into all such details, and once again telling you, go through your class notes, you will find complete details, right? So here, E equatorial and E axial, we have given only for short dipole. Do remember? Because in our CET and as well as NEET, 99.9% of the cases we always get short dipole. Therefore, I have given expressions only for short dipole. Right? Do remember this is for short dipole, right? Now, with these, from these two expressions, 2 to 3 important deductions that you can see immediately is, in the case of point charge, we have given E proportional to 1 by r square, right? But in the case of dipole, what you find, intensity versus distance, you will find E proportional to 1 by r cube. Inverse is there, but it is cube. That is inverse square, and this one is inverse cube. Do you remember? right? E proportional to 1 by r cube. And now here you can see from these two expressions, the difference is this number 2, right? And further I am telling you this simple reduction. Supposing same distance points, one is equatorial, other one is axial, both are at same distance. Of course, you should be knowing that the distance of a point from the dipole is always from center of the dipole. Repeat it. Distance of a point from a dipole means always from the center of the dipole. Right? Therefore, if distances are same, then intensity at axial point will be more. You will find intensity at axial point is double the intensity at equatorial point. Similarly, another example. Supposing we have same intensity. One intensity at the axial point I have taken, another intensity I have taken at the equatorial point. And supposing if it is given that E axial is equal to E equatorial, equate these two equations, and what is the simple result? R axial is cube root of 2. Observe carefully, it is cube root of 2 times R equatorial. And of course, the 2 rise 1 by 3. Cube root of 2 value is also nearly 1.12 you can take. 1.126 maybe if I am right. You can take that 1.126 you can take. Now this is one more very important case to be remembered, the expressions. Of course, having said that, the most important thing is about direction. Intensity of an electric field is always a vector quantity. Therefore, how to write a vector? Please observe carefully. Now I have to consider this point P1, which is an axial point. Axial point. At axial point, the field will always be along the axial line. Field along axial line, such that if the point is neither to negative charge, it is towards negative charge. Supposing same point, axial point, but it is on the other side, that is closer to positive charge, then what will be the direction? It will be away from the positive charge. So we'll find that what we find is E axial vector always parallel to dipole moment vector. Please do remember, intensity vector at any axial point is always parallel to dipole moment, and do remember how to write the directions. Now in the case of equatorial point, the intensity is given as 1 by 4 pi epsilon naught P by R cube, and the direction is parallel to axial line. Remember this, parallel to axial line from positive charge to negative charge. This is what is the vector. Parallel to axial line from positive charge to negative charge. So what is that you observe? That is E equatorial point is anti-parallel, opposite to dipole moment. So these are the important things to be remembered.